Yes. They have, there's, at one count, and it was a couple of years old already, but there were 200 different companies in the United States that sold chemicals for sealing concrete. Everything from Thompson's Water Seal to some pretty sophisticated stuff that 3M makes. But there's 200 different people that make chemicals to seal the surface of concrete, to make it last longer. You know, if any worked, you know, wouldn't it put somebody out of business? But what happened is they all fail in time. They all traffic off. They fail either because of wheel traffic or because of UV traffic or freeze thaw or something. And they're all superficial treatments, where what we're talking about here is actually making the concrete. You're making the concrete when you have a chance to do it right the first time. You can make it real low and permeable from the get-go. And longer life. That's exactly what they're trying to do. One way of looking at this is a life cycle model. This Life 365 model is software that was we helped pay for with Grace and Master Builders. It's actually an ACI document. ACI 365 is the committee that deals with predicting service life. And what this model has or allows you to do is build a structure and put it in a various part of the United States, build it with different types of concrete, turn the crank, and it'll tell you how long it'll last and how much it costed to last that long. Show you how that works. Real basically, it gives you a procedure where you can design a deck. In this case, I use the example of the Illinois Tollway 294. They have 8-inch thick slabs. They have 4% steel. Volume of steel is 4%. They've got 2 inches of clear cover over their concrete. What this model allows you to do is build a couple different cases. I tried to keep it simple and just use the base case and the high performance concrete that they are using. You could have 30 different cases if you wanted. The model knows the surface chloride chemistry for, in this case, Chicago. I didn't have one for Charleston. The nearest other place I think was Springfield, so I picked on Chicago instead. But it also has the temperature history per year, so it knows how much salt is going to hit that bridge. In this case, we said we want our bridges to last for 50 years. In this particular case, that was a design life. The one video we saw from New York, they said the original interstate system, when they started it in 1956, the average bridge lasted 35 years, which was great. When they started building the interstate system, they didn't have 18-wheelers. You know, they didn't have 80,000-pound trucks running down the highway pushing over 100,000 now. And they didn't have as many that were on the highway. And they probably had maybe 2% of the 18-wheelers back then in 1956. You didn't have the highways to carry them. So the highways you had were the windy 2-lane roads. You didn't put the big trucks on them because they weren't feasible. So there wasn't, there wasn't any 18-wheelers back then. So to have those bridges, even though they tried to design them with as much safety factors they could put into these bridges, the guys that designed the interstate system, they had some idea of what impact it was going to have on our economy, but it was only about half of the impact that it actually had on our economy. And now we know that if we do it right now we have a second chance to redo our bridges. We have a chance to make them last 50, 60, 75 years. They won't last forever, but they'll last more than what we got out of them the first time. And this is what this model tries to show here. The basic mix design, water-cement ratio, we actually can put in some dollars in this case to see what the model looks like when we run the exercise on this. Yard of concrete up in Chicago, that's probably light. It's probably closer to 150, 150, but I put 120 bucks. The model knows for this water cement ratio concrete, there's a certain diffusion coefficient built into that concrete. It has a certain permeability. That's the permeability number. It takes a certain amount of chloride concentration at the steel, 2 pounds per cubic yard, to start corrosion. So we've got to get 2 pounds of salt per cubic yard down to the steel in order to start corrosion. We're going to put epoxy coated bar on epoxy coating on our steel to try and make the steel from corroding. We said it's an electrochemical reaction. All epoxy coating is rubber coating this wire. You're coating the steel with a layer of non-conductive material to try and keep electrical current from hitting that rebar, that steel. That's all it does. It'll still start corroding when you get to 2 pounds per cubic yard of chlorides, but it'll corrode at a much slower rate. Gray steel without epoxy coating will have a propagation of only about 6 years before the structures, really fall apart bad. But epoxy bars will buy you about 20 years of life in that propagation part of the model. We had that initiation part and the propagation part. It's buying us extra time in that propagation part. The high performance concrete, we use the same water cement ratio, a little bit extra higher cost. We put silica fume and fly ash in it, had a big effect on the diffusion coefficient. We're still going to corrode at the same amount of chlorides if we can get them in there. And we're using epoxy bars. I said this is what they're actually doing up at 294. When we turn the crank on this model, it says that the base case is going to achieve our 2 pounds of chloride in 6 years, 8 years of normal use. Normal use in that area is that they throw, and I used to have a bag, 6 pounds of salt per square foot per winter. That's how much the DOT figures they actually throw on the 294 bridges. In the course of a whole winter, 6 pounds of salt end up on every square foot of bridge that they have on 294 over the course of winter. That's a lot. In the case of the high performance concrete, to get that same 0.2 factor, we're out here 20-some years, 24 years plus. If we turn the crank on this and actually run the economic model, we see that going in place, the initial cost, the high performance is a little bit expensive according to our model, but easily if we have a corrosion that's not going to happen until 27 years versus 7 years, and we put epoxy on top of it, we're going to last the 47 years before we have to repair that bridge versus half as much, versus 27, according to this particular model. We could tweak it, we could do other things, we could make this bridge last 100 years. We could use more cover, we could toughen up the mix, we could do various things for it. In this case, the goal was 50 years, which is what they achieved. That's what they wanted to afford. They're not worried so much about this thing lasting 100 years. This is in Chicago. They know they're going to overcapacity it before they get to 50 years. They just want it to last that long so that it doesn't fall down. They'd rather it be obsolete because of capacity, not able to carry all the vehicles that are going to be driving around up there in 50 years, but to have it last without repairs. Okay on this? Make sense a little bit? In the manual here, we said this manual, as y'all can read, is not for engineers. It's for contractors and the people in the field actually doing the work. Silica fume and this type of technology, we heard it said that it's been around for a couple thousand years, and it's been in this country since the mid-70s. I've been doing it since the early 80s, but there's still a large group in the construction industry that hasn't really embraced high performance yet. And sorry to say, it's the people that actually have to do the work. The engineers and the designers and the owners and the FHWA and the DOT and everybody else, they know what this can do. As they said 9 years ago, we know the numbers work, the models work. Now we have to get people to do the right things. It's a little bit different than regular concrete. We've seen some of the differences here in particle packing and those type aspects. What does that mean to the constructor? What does that mean to a ready mixer? What does he have to do differently with the way he's been doing business for the last 30 years? How does that change his life? That's all covered in this manual. That's a real how-to. It's written to that audience. It tells you how to set up your batch plants. If you're proportioning concrete, there's a very long, elaborate, formal engineering way of doing mix designs. Or if you have a good mix design that you know has already worked, use that as a starting point and just tweak it into your own. Again, technology transfer. Don't don't reinvent the wheel if you know you already have structures. In this case, table 6.2 in the manual is actually 2 pages worth of mix designs that across the top here gives you where it was used. A high-rise building, columns. Another high-rise building. A bridge mix in New York DOT. It's actually the mix that was on the video. A shotcrete mix. You want to use silica fume shotcrete. Here's a starting point of a mix design. The Hanford nuclear site, low heat of hydration, those mix designs. There's parking garages and a couple other mixes. Those are all starting points so that you don't have to reinvent the wheel. Because this is an FHWA publication, that table's all in kilograms per cubic meter. But if you go to the back of the book in the appendix, all the tables are in pounds per cubic yard. They're all in our language.
These recipes are public domain?
The mixed designs? Yes.
Kind of recipes that you don't do it?
These are mixed designs that have been published in technical papers. All of these structures that are listed here have all been, documented and discussed and studied. And so yes, the mixed designs are all in public domain. They're only starting points because you have to incorporate your own aggregates. And your own aggregates, the sands are going to be different, the limestones or gravels are going to be different. You have to tweak your mix design for your own materials anyhow. These are just starting points so that we don't have to start over from those very laborious engineering practices of coming up with a mix design. We already have good ones. Let's start with these and just tweak them. And how we tweak them is they have the book goes through a step-by-step procedure. I think there's 6 different steps here of how to take one of those mixed designs and turn it into your own. Again, I said it's written, it's real practical. Producing it at a ready mix plant, there's a chapter on chapter 7 here. Setting up silos to handle silica fume is a little bit different. We saw the materials obviously lighter. We found out that there's another property to the material that is pretty unique. It has an electrical charge, not an electrical charge, more magnetic charge, that happens to be at the opposite end of the spectrum as steel. So if these pipes, from blowing it from a truck and blowing it into a silo, blowing it through these small confined spaces, we found that if you blow it through steel, it has a tendency to want to stick to the walls just from this magnetic attraction. And once it starts sticking, it just builds up on there. But they found that by using rubber and silica fume are at the same end of the magnetic spectrum. So it's like 2 negative poles repelling each other. You can blow it through rubber all day long and never packs up on it. So one of the little tricks here setting up a plant for handling this material is the guys have to get rid of their steel pipes. Their rubber works better. The material is also used in bags. Some of these bags are actually repulpable, which is what they're doing here that allow you to just dump the whole bag into the concrete truck. The paper is designed to actually shred up with the aggregate, to beat it up, and actually dissolve back into cellulose fibers. Doesn't dissolve, it repulps. The aggregate beats the paper back into its cellulose fibers. It doesn't work on all mixes. If you're dealing with overlay mixes where the aggregate is real small, 1/2-inch aggregate, pea gravel, number 8s, those type things, the aggregate's probably not, in the mixture, is probably not impacting the paper enough to really do the shredding. So the manual goes into great detail of what mix designs these bags can be thrown in on, or some mix designs where we're doing overlays where there's real you may have to dump the contents into the back of the mixer. But it comes in bag form, it comes in bulk form. The major work that's going up in Chicago and all the high-rise buildings, they work with it out of silos. The Interstate 70 here, as it crosses the border from Indiana into Illinois, those bridges were all repaired with this concrete in 03, 02. That was actually done with bags because bridges use a little bit less volume of concrete than a big high-rise would. So it comes in different forms, but the manual will go into detail step by step of how to do it right.